Welcome to lecture number 29 for ECE 461 Control Systems, Z-Transforms. Now, back when you took signals and systems, you covered Laplace transforms, Fourier transforms, and Z-Transforms. Z-Transforms always cause confusion. They're actually extremely useful. What the Z-Transform does is it's the way to represent the basically software. Laplace transforms describes RLC circuits. A capacitor is an integrator, I equals C dV dt. Inductors are differentiators, B is L di dt. So any circuit that has capacitors and inductors is described by differential equations. Likewise, you use Laplace transforms. If instead I use a microprocessor, then I really need to use Z-transforms. So whenever you see a transfer function in S, think capacitors, inductors. Anytime you see a transfer function in Z, think microprocessors. And the idea is if I have a compensator, I can implement it using capacitors like we did in some of the circuits before. I can design lead compensators, PI compensators, all with op-amp circuits. Anything I can do in hardware, I can do in software. I could also take that circuit and replace it with a microprocessor. The nice thing about that is I can just implement code to design the feedback controller. If I want to change the system, change the code. And actually that's kind of one way that some systems are built. In the research labs, they'll typically have a very high performance assembly line or things like that. And the compensator can make the assembly line look like a lower quality brand that you'll see on the assembly line. Or I can take a jet aircraft, a high performance jet aircraft, change the feedback controller, make it look like a Cessna, make it look like a Piper Cub, make it look like a MiG, all by just changing software. So this is very versatile. And it's actually how most feedback controllers are implemented nowadays. Microprocessors are so small, so cheap, so powerful. This is a very good solution to many problems. The challenge, however, is since this is a microprocessor, you really need to analyze it in the Z-plane, not the Laplace plane. So the next couple lectures we'll look at how do you design feedback controllers in the Z-plane. And you'll find that the math doesn't care. If I have a feedback loop, is it S, is it Z, is it W? It doesn't care. It just cares about the roots. How you interpret the results, though, does depend upon what plane you're in. If I'm in the S plane, right half plane is unstable, left half plane is stable. In the Z plane, the unit circle is the dividing line. So we'll be looking at how do you design, or first, given a system G of S, how do you convert it to the Z plane, and then how do you design feedback controllers using root locus techniques in the Z plane. So that's what we'll be doing for the next couple lectures. The approach that we'll be doing is as follows. This is how it's actually implemented. I've got an analog plant that's a motor, temperature, rocket. There's some system described by differential equation. I've got the microprocessor that's described in the Z-plane. To connect the two, I have an A to D, D to A converter. So what happens is the analog, the real world is running out here in the analog time. I sample the input every t seconds. The A to D converter converts that to a digital number the microprocessor can read. You then do some number crunching. Take the results, spit it out to a D to A converter, and that's the analog U. That drives the plant, which then changes the output, take the difference, next sample, repeat. Relative to the microprocessor, the world looks like a discrete time system. I spit out an output. 10 milliseconds later, I get an input. Spit out an output, 10 milliseconds later, get an input. So the microprocessor thinks the world is discrete. So one way to design the system is change the problem. What does the world look like relative to the microprocessor? The advantage is now everything's in the Z-plane. I can analyze systems in the Z-plane. What's really hard is a hybrid system like this. This is actually how it's implemented. A hybrid system where you have Z-plane and S-plane all mixed together is kind of hard to analyze. So we change the problem so that you're consistent. Everything's in the Z-plane. That's one way to do it. Second approach we'll be looking at is trying to analyze this system as is, and mixing Z-plane and S-plane. You can do it. But we'll get to that in a couple lectures. So that's where we're heading. And again, the reason you want to use a microcontroller is, you've probably seen this in labs. If you have a circuit that's built, circuits that worked yesterday may or may not work today. Software, on the other hand, software that ran yesterday should run today. unless you have automatic updates. In software, you don't have DC offsets. Op-amps are notorious for having a slight DC offset, so even if I have an integrator, the output may not track exactly unless I can zero out that DC offset. With a microprocessor, 0 plus 0 equals 0. You don't have problems with those DC offsets. Another advantage is the circuits we've been looking at, I can design a lead compensator to cancel a real pole. I've got problems when it comes to complex poles. I don't know where to put or how to design a circuit that has complex zeros. In contrast, in the Z-plane, you don't really care. It's just what's a polynomial, do a bunch of multiplies and adds. If the polynomial has real roots, that's nice. If it has complex roots, that's nice. I don't care. So real poles, real zeros, complex poles, complex zeros are easy to do with the microprocessor. And finally, if you want to change the controller, just download a new program. So it's way easier than trying to build a new circuit. The problem with microcontrollers is it's easy to implement difference equations k of z, but it's very hard to implement differential equations k of s. So what I'd like to do is design my compensator in the z-plane. And to illustrate how it's easy to implement compensators in the z-plane, take the following difference equation. This is what a typical controller is going to look like. I have this infinite loop. Against the infinite loop because I want it to work over and over again. It's like a stoplight. I don't want a stoplight to work once. I want it to keep on working over and over again. If I'm trying to control an airplane, I want to keep it level and flying forever, not just once. So here's an infinite loop. It's always running. I'm going to keep track of how many times I've gone through that loop. That's time. Iteration number 1, 2, 3, 4. Each loop, I'll read the analog input and remember its previous value. I'll calculate the current output and remember the previous output. And the way I calculate the current output is the previous output plus 0.2 times the current input minus 0.9 times the input one sample ago. That's the difference equation. This is how you implement this code. That's really how most controllers are implemented in software. Notice this is a difference equation. Y of k is the function of the previous values of the output and the input. It's not a differential equation, it's a difference equation. Laplace transforms doesn't describe this really well. Z transforms do, which is the reason I want to use Z transforms. To get into Z transforms are similar to Laplace transforms. It's based upon the assumption you make. With Laplace transforms, I assume everything's e to the st. The reason I do that is when I differentiate, I get s e to the st. So with this assumption, differentiation becomes multiplication by s. And the assumption is algebra is easier than calculus. So I can now use algebra with s's rather than calculus with differential equations. For example, if I have this transfer function, what it means is cross multiply. S means derivative. This transfer function means that x and y are related by that differential equation. Or conversely, if I have x and y related by a differential equation, I can give it a transfer function. And note that the transfer function is an s. And the order of s tells you the order of the differential equation. Now in contrast, Z transforms assumes everything's in the form of z to the k. What that does for you is if I have a difference equation, say y of k plus 1, move forward in time by one sample, that becomes z to the k plus 1, which is z times z to the k, which is z times y. So in the Laplace domain, sy means the derivative of y. In the z-plane, zy means the next value of y. And Z transforms turn difference equations into algebraic equations in Z. And very similar to Laplace transform. And I mentioned earlier that writing a program to implement k of s is hard, but a program to implement k of z is easy. For example, if I had k of z as some generic third-order polynomial or transfer function, cross multiply, solve for the highest power of y, gives you z cubed y. What this means is zy is the next value of y. Z cubed is y 3 samples in the future. Z squared is y 2 samples in the future. Z is y 1 sample in the future. This difference equation is the same as that transfer function. If I do a change in variable and shift everything by 3, so I no longer have y of k plus 3, I have y of k, the present output, is a function of the previous output, 2 samples ago, 3 samples ago, and the inputs. Solve for the current output, and the current output is a function of the previous outputs, the current input, and the previous inputs. This I can implement. That's my code. The way you write the code is I have to remember what was the input 3 samples ago, 2 samples ago, 1 sample ago, and the current input. And I got to remember up to 3 samples in the past. I need to remember the output 3 samples in the past. So remember the output 3 samples ago, 2 samples ago, 1 sample ago. Now the current output, y0. The current output is a function of the previous outputs and the previous inputs. And note, this equation right here is basically the only line of code you ever need to change. Change your difference equation, change that one line of code, I've got a new program. I've got a new filter. The thing to note is this code right here exactly implements that transfer function in Z. That's why I want to come up with my compensators in the Z-plane. If it's in the Z-plane, I can implement it exactly. In contrast, if I had this transfer function, implement that in software, to do that I'd have to use numerical integration. I'll have to do integration twice. Integration is not perfect. I've got problems. There are no problems here. This is exact. For example, let's give a hard example. Suppose I had the following filter. If that's my compensator k of z, to implement it, multiply out the polynomials, cross multiply, solve for the highest power of y, divide through by z squared, and there's my output. The current output of my filter is 1.5 times the previous output, minus 0.5 times the output 2 samples ago, plus 0.2 times the current input, minus 0.9 times the previous input. So again, this is, you can almost write that by inspection, multiply it out, there's your denominator polynomial with a minus sign, and here's the numerator polynomial. In code, I just have to remember this goes up to 2 in the past. What's the input 2 samples in the past? What's the output 2 samples in the past? And the current output is a function of the previous outputs and previous inputs. So we just need a couple multiplies and adds. A couple things to note. I can implement a compensator in the z-plane exactly. There is no approximation. That's why I like the z-plane. If I want to change the filter, just change one line of code. Everything else in this program stays the same. Change that one line of code, I can have a new filter. Be it a PID, lead, lag, you take your pick. Complex poles and zeros are very easy to implement. Note back here. These could be real roots, they could be complex roots. I don't really care. All they do is they just change the numbers that you multiply. Again, these are going to be real numbers. I don't really care what the roots of the polynomials are for implementation. So real roots, real poles, complex poles, not a problem. And the order of the filter determines how far in the back you have to go. A third order filter means I use data from 3 samples in the past. A fourth order filter means I use data from 4 samples in the past. Also, in the S-plane, you try to keep your compensator so that I have as many poles as zeros. The reason being is if I have more zeros than poles, I'm differentiating, and differentiation creates noise amplification. Think of it, most signals are at DC, noise is at high frequencies. If I multiply by S, the low frequency gain is 0, the high frequency gain is large. I'm amplifying the noise. So differentiators are great noise amplifiers. You try to avoid those. In the Z-plane, if I have more zeros than poles, I'm predicting the future. Z means the next value of. If my filter is Zx, that means I want to output the future value of X. So far, no one's ever been able to predict the future like that. If you can, take me to Vegas with you. We'll make lots of money in slots. Actually, probably more like roulette. But again, you can't build non-causal filters in the Z-plane. I don't like to build filters that have more zeros than poles in the S-plane. I can do it, but I don't like to. Either way, you try to avoid having more zeros than poles. In the Z-plane, you must not have more zeros than poles. Also, you've got to have integer powers of S. Sy means the derivative of y. If I have s to the 0.3, that means I take the 0.3 derivative. And I don't know what a 0.3 derivative is. I can take one derivative, I can take two derivatives. I don't know how to take a third of a derivative. So you're stuck with integer values for s. Same thing in the z-plane. Z inverse means the previous value of y. I've got a subroutine being called every 10 milliseconds. Zy means what was y last time I called the subroutine. Z to the minus 2y means what was y 2 samples in the past. So z to the minus 1 makes sense, z to the minus 2 makes sense, z to the minus 0.3 means what was y a third of a subroutine call in the past, and I don't know what a third of a subroutine call is. So again, you kind of have integer powers of z. There's also a relationship between the s-plane and z-plane. Laplace assumes everything's e to the st. Z assumes everything is z to the k. Well, let's assume t is equal to kt. K is my sample number. T is the sampling time, like 10 milliseconds. If I substitute, y of kt is e to the s times kt. Group these together, that's e to the st to the k. That's z to the k. That's the conversion between the s-plane and z-plane. Z is e to the st. That's very useful. We're going to be using that a lot. That lets me do things like analyze filters in the z-plane. A little bit of background. In the s-plane, if I have a filter and the input's a sine wave, that's a phasor problem. This is true for all s. All I care about is what's the gain at s equals j4. So I convert x to phasor form. That's 0 cosine, 3 sine, 0 minus j3. S is j4. That's the frequency of the sine wave. Then the output is gain times input. This is the gain everywhere. All I care about is what's the gain at j4. Here's the input at j4. There's the output at j4. And again, what this means, real part is cosine, minus j is sine. So that's how you analyze filters in the s-plane. Z-plane is the same thing. Here's the filter in the z-plane. It's not obvious, but that's actually a filter. If my input's a sine wave, the output's a sine wave. To find out what the output is, do about the same thing. Convert to phasors. X is 0 minus j3, 0 cosine, 3 sine. S is j4, and z is e to the st. That's the connection between s-plane and z-plane. S is j4, t is 10 milliseconds, so there's z. This is true everywhere. All I care about is what's the gain at z is 1 at 2.29 degrees, times the input at that frequency, gives you a complex number. Real part's cosine, minus j is sine. It's not obvious this is a filter, but if you try it, say throw it in VisSim, here's my sine wave, there's my filter. The output is also a sine wave. These little stair steps you see, that's my sampling time. But the output has a phase shift, a delay, changes in amplitude. Phase shift and a change in amplitude is a complex number in polar form. That's a complex number. Change the frequency, I'll have a different output. So z-plane is just like the s-plane. This is a filter. And it kind of makes sense. Anything I can do in hardware, I can do in software. If I have a filter in the s-plane, there's a program that can also implement it. We'll talk about that later, next lecture. But this is a filter. If I have a sine wave input, that's the way you analyze it, use phasor analysis. If I have a step input, I need to use Laplace transforms in s-plane, z transforms for microprocessors. To solve for the step response, I need to use a lookup table. So let's do like we did in the s-plane. In the s-plane, I had the lookup table for delta function, step, and I think a damped sine wave. Same thing as z-plane. Let's start out, let's just assume that the z transform of a delta function is 1. When you took signals, there's a proof of that. We'll just kind of take that for granted now. What a delta function means, this is 1 at k equals 0, 0 otherwise. That's a delta function. Z transform is 1. Let's take a unit step. To find the z transform of a unit step is 0 for k less than 0, 1 for k greater than 0. Let's delay a step. 1 over z times u of k is u of k delayed by 1. Now take the difference. These all cancel, and I'm left with a delta function. I know the z transform of a delta is 1. So 1 minus 1 over z times u is 1. Solving for u, the z transform of u of k is z over z minus 1. So there's the z transform of a step. If I have a decaying exponential, this would be 1, a squared, a cubed, and so on. If I were to delay this and multiply by a, I now get 1 delayed times a becomes a delayed times a times gives you a squared. I get this. Take the difference, I get a delta. Meaning that 1 minus a over z times x is 1. Take the z transform. Solving for x is z over z minus a. This is the z transform of a decaying exponential. And if I let a be a complex number, do a little bit of algebra, I get a damped sine wave. So this is the lookup table. From my experience, this is really all you need for the z transforms. Delta, step, exponential, and damped exponential. And if you're wondering, to use that, suppose I want to say, here's my system, g of z. Find the step response of g of z. So I take g of z times the step, z over z minus 1. Now, this is not in my table up here, but a single pole is in my table. So let's use partial fractions. Let's factor out a z. The reason I do that is there's always a z in the numerator for my table. So I want to leave a z in the numerator, pull that out, and take the partial fraction expansion for the middle, and I get these three terms. And again, for like the z minus 0.9 term, to use the cover-up method. Plug in z as 0.9, so 0.2 times z over z minus 1 over z minus 5. When z is 0.9, it gives you minus 4.5. Partial fractions. Multiply through by z again. These are in my table. This becomes 4 minus 4.5 times 0.9 to the k plus 0.5 times 0.5 to the k for k positive. That's why I have k. If I have complex poles, again, it's not that hard. Bring this inside, factor out a z, do partial fraction expansion. When I do that, I'm going to get a complex number. Polar form works a little bit better. In polar form, twice this will be the amplitude. The amplitude of the pole is your 0.9 to the k. The angle is the frequency. This changes by 10 degrees every sample. 36 samples gives you 360 degrees one cycle. And turns out the angle over the negative term is your phase shift. And note that in the S-plane, rectangular coordinates work best. Real part is the exponential, complex part's the frequency. In the Z-plane, polar works best. The amplitude of your pole is the rate at which it decays, and the angle is the frequency of oscillation. Last example, which you can also do with Z-transforms, is take business classes. Time value of money is really a Z-transform. For example, suppose I borrow $100,000 at 6% interest, meaning 0.5% per month. First off, I'm getting ripped off. That's a high interest rate today. But assuming I did that, and I want to know what the monthly payments are, that's the Z-transform problem. The loan value for next month is the loan value for this month plus 0.5% minus how much I paid plus the initial loan. And so this is, I'm going to borrow $100,000 at k equals 0, and that's it. That's my delta function. Now take the Z-transform. X of k plus 1 is zx. X of k is x. P is p times a constant. A constant is the unit step. Pz over z minus 1. This assumes I'm making a payment at time equals 0. If I skip the first month, that'd be 1 over z minus 1 plus my initial loan. Solve for x, and I get this. Do partial fraction expansion. Take the inverse Z-transform. And my endpoint constraint is that k equals 10 years, k equals 120. The loan's paid off. So that'll be 0 is 1.05 to the 120 times the initial value minus 200 times 1.05 to the k minus 1. Solve for p. The payments are $1,110.20. That's really what a business calculator does. A business calculator, you plug in the loan amount, the interest rates, the number of payments, and it calculates the monthly payments. The way it does that is C transforms. So now you can actually do analysis like they do in business, just using a regular calculator. That gives you some background on Z transforms. We'll be using these in the next couple of lectures to analyze how do you design a compensator for a plant, but pick a discrete time compensator, pick a compensator in the Z-plane so that I can implement it in software. That's lecture number 29, Z transforms for ECE 461.